This is my Lab 9 for Physics 2211. The main purpose of this lab was create a model of a spring pulled in 2 dimensions using the energy and momentum principles. I was able to create the model by changing a little bit of the code. There's still conservation of energy. The model is better at the beginning of the time period. So the experiment probably has some sort of energy loss. The mass of the ball was 0.402 kilograms. The initial position ball was negative 0.104 and negative 0.642 in the y direction. And that was having the origin where the spring is connected. The spring constant was 6.87 Newton meters, which was determined in the last lab. And the initial initial length of the spring was 0.127. So to determine the position, I calculated the force of gravity, just mass of the ball times the constant of gravity. And then also calculated the force of the spring, so negative the spring constant times stretch, which was the magnitude of the length of the spring at any given point minus the initial length of the spring times the direction vector of the length of the spring. And adding those together, you get Fnet. Apply it to determine the change in the velocity of the ball, and then use the velocity to calculate the change in position. So I also calculated the change in spring potential, which was 1/2 times k times the magnitude of the length minus initial length. And I also calculated the kinetic energy in the gravitational potential by taking the mass of the ball times constant of gravity times the y position, and the kinetic energy was 1/2 times the mass of the ball times the magnitude of the velocity, which is speed squared. So if we run this, the blue is the experimental, and the orange is the model. The y values here, this is the y values. The green is the experimental, and the red is the model. So they're pretty good. It gets worse as time goes on. The same thing with X. It's pretty good. It gets worse as time goes on, and the peaks don't line up here exactly. So using this data, I was able to calculate the periods by taking one peak minus another peak. And the period of X for the model was 1.72 seconds. The period of Y in the model is 1.518 seconds. In the experiment, the period for X was 1.71 seconds, and the period of Y was 1.61 seconds. They're not the same, mainly because there's some sort of pendulum motion in there too. So the length of the pendulum is constantly changing, and that adds some complexity to the system. The pendulum period is calculated by the length, and it's this length that's constantly changing, and they don't exactly line up. The periods are different. So in this model, work was 0 because we used the change in spring potential also. So we assume that there's no work done. Realistically, there's probably some air resistance or loss of heat, but we assumed in all that work was 0. So if we change the gravitational potential by adding 0.17, the length that I determined in the first lab to be the equilibrium length of 0.7 meters to the y position when calculating the gravitational potential, it will increase the gravitational potential energy and the total energy of the system but the change in total energy and the change in gravitational energy will remain the same, and it won't affect the other two energies.